建构无限多的 solution。对，那 the same concept applies to system of linear equations. If you have more than one solution, say you have two solutions. As long as you have two solutions, you can use those two solutions to construct infinite number of solutions to satisfy every linear equation, right? Right? So originally, say like in terms of the number of possible cases, you have like no solution. And one solution. And then two solutions. And then n solution. And the other is just infinite solution. But in our previous discussion, we just discussed, all these things converge into infinite solutions, right? Right? 只要你有两个 solution， 对这个 linear system linear equations， 那你用这两个 solution， 同样嘛，就是 u 加上 c 括弧 1减 u， 你是不是就可以建构出来？就选不一样的 c， 然后就可以建构出来无限的这个 solution， 对不对？那这些所有的这个 solution 都可以 satisfy 每一个 linear equation。那这样子的话，是不是这些通通都有一个 solution？ 所以就 no solution， one solution， 就只有这三个 case， they are only the cases。Okay? From your logic, okay, from the logic that you have learned in discrete math. Okay. 所以你在学 discrete math, you may not know where to apply those knowledge. No, this is the example. You apply discrete math knowledge in linear equation. Okay? So system really, of course, it's still geometric. It still means okay, all these because each of these equation, in some sense, it represents certain shape. In if you have n variable, that's n dimensional, right? Okay, each linear equation represents certain shape. Actually, it's a hyperplane, but let's forget about that. Okay, let's just imagine it's a shape in like an n-dimensional space, and the solution, as you have seen in the previous slide, is like the intersection, right? Still, everything applies in n dimension, even in n dimension. So if you have exact one solution, that means all these n shapes eventually intersect the intersection of these n shapes. Okay, is one point. Okay, or okay, all these shapes, they have intersection is it is either a line or a certain even set, or they do not have that intersection is empty. Okay, so there's no solution. It's just you cannot draw it. You cannot draw it on two-dimensional space, unfortunately, because n dimension you just cannot draw it. Two-dimension, three-dimension, you can still either draw it or imagine, but more than three-dimension, probably. But the idea, okay, the geometric idea still apply. Okay? So a system of linear equation is called consistent. It has at least one solution. And inconsistent, it has no solution. So now look, okay? The first two cases, if the system of linear equations, okay, belong to the first or second cases, then we call such a system consistent. Otherwise, if the system of linear equation has no solution, it's still the case, then we say it's inconsistent. Just want you to understand this terminology, okay? Then, okay, it comes to high school, probably not in high school, like in junior high school. When your teacher teach you how to solve the system of linear equation, they will teach you to convert your system into we call row echelon form. What is row echelon form? Okay. The row echelon form, okay, follow a stair-step pattern, like this, stair-step pattern. Okay, and it has leading coefficient 1. So the first coefficient, the leading variable, the coefficient is 1. Okay. So all variables are aligned. Okay, we try to put them aligned. And in an equation, okay, the leading coefficient is the coefficient of the first variable. We already talked about the coefficient. So from the left-hand side, it's not row echelon form. Okay, obviously it's not stair, like a stair step, and it's not a stair step pattern. The right-hand side is row echelon form. Because the stair step pattern, like每一层下面就是往后面多出至少一个 the leading coefficient are all one. Okay. And if a system of linear equation is not row echelon form, you can obviously convert it into row echelon form. Okay. So before we talk about that, okay, how do we solve a row echelon system? So it would be very easy if your system is already in row echelon form. Basically, we just use back substitution. So, for example, this is an example. Okay, this is row echelon form. So Z is true. So when Z is true, mark it 2 here for Z, and you get Y is negative 1. Okay, and if Y is negative 1, Z is 2. Mark it these two values, and you get your X value, which is 1. Okay, so the idea works pretty well for row echelon system. Okay? And how do we convert a non-row echelon system linear equations into row echelon? Basically, we use Gaussian elimination. Okay. In junior high school, when your teacher teach you this, your teacher may not tell you this is Gaussian elimination. Or maybe he or she may have talked about this, but it was a long time ago, you already forgot. Okay? But anyway, now you know, like, what the Gaussian elimination is. Okay? Basically, okay, first, when you talk about equivalent systems, two systems of linear equation are equivalent if they have precisely the same set of solutions. Okay? So the operations that will produce the equivalent system include exchange two equations. The exchanging two equations does not change the solution space, right? Obviously, right? This is easy. multiply the equation by a non-zero constant, okay, again, you can come back, right? If you multiply a constant c, non-zero constant c, you can always multiply like 1 over c to return it back to original shape, right? 因为你可以过去可以回来，所以说 ，OK， 这样子的 solution， this operation does not change the solution space. The third one is a little tricky. Add a multiple of an equation to another equation. Add a multiple of an equation to another equation. So it's like so you have like an equation. And then, for example, you multiply this equation by a constant c, and then add to this one. Okay, add to this one. So let me just use like some. This is a circle. This is a triangle. This is a square. This is a box. Okay. So if this is original equation, then after this operation, it becomes circle, triangle. This becomes like a square plus c times triangle, right? And that's why it stays the same, right? Right? I mean, I'm too lazy to write down the whole thing, but you can do it, right? Later on, you will learn more and more on how lazy I am. Anyway, okay. Here, okay, obviously, you can multiply by a negative c, and then add it to here to convert it back to an original shape, right? You know what I'm saying? The main idea is that does this operation reversible? Is this operation reversible? If it is reversible, then it does not change the solution space. Okay? So if you multiply the equation by constant, here, I mean, this constant, it could be even 0. When it's 0, obviously, it does not change it, right? Okay, it's a really different from the second operation. Okay, so this c can be any variable, any constant. Okay, so multiply this equation by add to the other equation. This operation, okay, can be exactly reversed. Okay, I'm just showing you that. Okay, because of that, so suppose this operation shouldn't change the solution space. Okay, and with that in mind, okay, once you have these three operations at hand, we can talk about Gaussian elimination. Okay, the Gaussian elimination, the purpose of Gaussian elimination is to rewrite a system to an equivalent row echelon system by a sequence of these three operations. Okay? So let's have a look at the example. Okay? So here is a non-row echelon form of system. So first, okay, we try to eliminate the second one, the second row. Okay? Because the first row, the leading coefficient is already 1. If the leading coefficient is not 1, we need to make it 1. Okay, if it's say it is 2 or 3, you can divide the whole equation by 3 to make the leading coefficient 1. You may ask, how about if the leading coefficient is not 1? It is 0. If the leading coefficient is 0, I mean there's no x1. Okay, in the first equation, then we can switch to a spot. Okay, to remove like the equation that has the coefficient of the non-zero coefficient for the first variable to the first one. Okay, but you get an idea. So but here, okay, for this case, the leading coefficient is already 1, and then we just like try to eliminate the leading variable. So we add we just add we multiply the first equation by 1 and add to the second equation, and by doing so we eliminate the negative parts in the second equation. So it becomes like y plus 4, and then we multiply the first equation by -2, and then add to the third row, and by doing so we eliminate this one. So we become like this. And here, leading coefficient for the second equation is only 1. Okay, so we are lucky. So then we just like multiply this equation by 1, and then add to the third row. So we get the row. So now this 2 is equal to 4. Obviously, this leading coefficient is not 1. So we need to divide this equation by 2. Well, so now we have row echelon row. And all these operations belong to these 3 operations. So we know that all these systems are equivalent. Now their solution space are the same. Okay? So you should have learned this in your either junior high or high school. Okay? I mean, otherwise, how do you solve the system linear equations in your young age, right? Okay. So, but it's just like at that time, they may not tell you the terminology. Okay, so let's take a break, and then 10 minutes break, we'll come back to the discussion.